All right, here we go, ladies and gentlemen, my virtual students at home. Today's lesson, we're going to continue with scatter plots. Now we're going to talk about lines of best fit. Now this is how we can make better, more precise predictions based on data that we record and the relationships that we see. Now you'll notice at the very top of the page here, you see at the top, um, we've got our standard for Indiana. It's 8th grade data, statistics and probability. Standard number 2, and it says, know that straight lines are widely used to model relationships between two quantitative variables. For scatter plots that suggest a linear association, we informally fit a straight line, and I want to bring this to your attention as this will make a lot more sense um, as we get further into the lesson. But informally, which means it's an approximation, okay? And we're going to make it fit the pattern the best that we can. And then we can describe the model fit by judging the closeness of the data points to the line. And it goes back to what we talked about with scatter plots the last couple times. The stronger the relationship, the more the points fall into a linear model, the better that our line will be. And the more loosely they fit, the weaker the association, then it's going to be it's going to model what we're doing, but there's going to be a little more room for interpretation. Okay, so let's take a look at some questions here, um, real quick. Just kind of rolling into it. Okay, let's just read out our book. It says, this table shows the average annual cost of 1 pound of chocolate chip cookies. It says years since 2000. You got year 0, 1, 2, 3, 4, 5, up through 9. And you got the prices from 2000, $2.59. And it changes each year. You can see it's the average. So it says, what year corresponds to 0 years since 2000? Well, if it's been 0 years since 2000, that would mean that it's still the year 2000. This is something different for students that you can have. How can a year be 0? Well, it says years since 2000. So that would mean this is still 2000 right here. This is when we started. In 2000, the average price of a pound of chocolate cookies is $2.59. So then what year would it be 9 years since 2000? Well, 9 years later. What's 9 years after 2000? Should be straightforward. It should be 2009. Now here's something I want you to think about. It says, if the data were displayed in a scatter plot, would the scatter plot show a positive, a negative, or no association? I want you to explain. You might be going, I don't really know. Well, take a look. What's happening with the price? Well, it went up, then it went down. Then it went up, and down and up, then up a little more, and up a lot, and up. So in general terms, the price tends to go up most of the time, which would suggest it's going to have an upward slant or a positive um, association. But who knows? You know how we can find out for sure? Let's make a scatter plot. Now what you're going to see as we take a look at the next page, the book's already done the scatter plot, and they even draw this best fit line, which I'm going to explain to you right now. Okay, so let's move on. See, up here at the top, let's focus on first. It says, when data are collected, the points graphed usually do not form a straight line, but may approximate a linear relationship. And we've talked about that. If they fall into a perfectly straight line, wow. Because in the wonderful world of research, where this is really from, I mean, this is what we use to figure out patterns and to figure out relationships. Okay? If that happens, wow, it's just usually it doesn't. It can be close, but that's what we'll see. A line of best fit is a line that's very close to most of the points, and that's what I want to talk to you about. Because look, this is taking you off the hook right away. The line of best fit is a line that is very close to most of the data points. And I'm going to explain how we do that. So it says, refer to the information in a table about the cost of cookies. So it said, construct a scatter plot using the data. Now, we've talked about this, and we'll be doing some scatter plot construction, but I'm hoping you know the years, that's going to be on the x-axis, the cost is going to be on the y-axis, and we're going to plot these on a grid. Now, this grid that our book uses is kind of wonky looking because it's got rectangular grids, but it'll be okay. So it says graph each of the data points. So they did. Look, you can see it right here. Year since 2000, that's our X. All right. Average cost, that's our Y. Okay. Because the cost depends on the year we're talking about. So you graph the data points. Now, right now, ignore this blue line. Pretend it's not there. Because if you look, and I wish they hadn't drawn it there, but we're gonna do some of this ourselves anyway. Okay. As we look at this, we're going to draw a line that fits. Well, if you notice, these points don't fall into a nice tight straight line. In fact, the pattern, and I'm going to use blue, or yeah, let's use blue. The pattern is they're kind of spread out. It's kind of loose. Okay, if you look, the pattern, I mean, it kind of goes this way, but look, oops, I mean, there we go. That's better. If you look, it's just kind of this wide pattern, right? And that's what I want you to focus on. That those dots, there's even that one that's sticking out a little further, but that's okay. You get the general idea. Most of them fall into this. It's linear pattern, but it's kind of spread out, isn't it? So it's a little loose. It's not real strong. It's a little weaker of an association. But you notice now, look where that straight blue line is drawn. You notice how it kind of just goes right down the middle of that. Remember, it's an approximation. Okay, it's not going to be perfect. We're not playing connect the dots. In fact, they didn't have to draw it through this dot right here. Okay, but they did since that was your zero. They're like, okay, and it kind of fits. It's kind of sitting in the middle. I mean, it could have been up here, but that'll do. Okay, so the line, this best fit line, kind of goes right through the middle. Not quite half the points are above it because there's 9 points. So you got about 5 dots below it, 4 dots above it. That's a line of best fit. Okay, that's what we do. From that, we say, okay, this reflects the general pattern because okay, some of the points are above it, some are below it, so they'll kind of cancel each other out. So that middle ground's a good place to live. Okay, and we're going to do this ourselves in just a moment, so it'll make more sense. Now, if you go down here and you look, this next question says, use the line of best fit to make a conjecture about the cost of cookies in 2013. Well, if this pattern continues, it looks like the price of chocolate chip cookies are going up by the pound, right? Now, the question is, where's 2013? Well, I'm looking, 2013, that'd be 13 years after 2000. So 2, 4, 6, 8, 10, 12, 14. So 2013 is like right in between these two. All right, in fact, I'm going to make this easier for you guys to see. Use the arrows. And let's go red so it stands out. So basically, we'd look and see, well, where's this line? What's it hitting? So if I go straight up, that's where I'm looking, okay? So I'm not actually going to draw this line. I'm using it to see. Oh, right here it hits, so I'm going to read over to that one. Okay, so I'm looking over here from this point going, well, what's that going to be? Well, it looks like it's right between $3.30 and $3.40. So based on this, our conjecture, notice it's conjecture, it's not stone cold fact, it's just an idea. That makes it look like, well, then in 2013, the average price of chocolate chip cookies should be somewhere around $3.35 a pound, okay, based on this information. It gives us an idea. It's a projection, really. It's a projection. And this kind of stuff happens all the time. Okay? Collecting data to make predictions. I mean, it happens big time on a daily basis in stocks and bonds and things like that. Okay? Let's take a look at another example and we'll actually do the work. Okay? It says, refer to the scatter plot about yearly points scored by a certain race car driver. So here's the scatter plot. Okay, draw and assess a line that seems to best represent the data. Well, look. See this point way down here? That's kind of way off. All right? I'm looking at that going, you know, so we're going to make conjecture. So we look at this pattern. Well, again, like, well, do I follow this? I mean, it's not really a straight line. Yeah, you have to look at the whole thing. Okay, what general pattern does it make? So allow me to go back to my highlighter. So when I look at this, I'm kind of looking at all of this. If you look, it kind of does, whoops, most of the points kind of fall into that, don't they? Okay, I mean, we can get a little crazy and say, okay, let's go like this. That, most of his points, you got this one lonely one down here, but you could almost consider that an outlier. So we're looking at making a conjecture of what the driver will score in 2015. Now this is years since 1999. So the best fit line, you would draw a straight line that kind of cuts right down the middle of this wide path. Okay? It may hit a dot or two, it might not hit a dot or two. Okay? But in this case, I'm looking going, okay, middle of this path looks to me like about right here. Does that seem reasonable? You know, best fit line, that's what we're going for. All right? Now, that's how we draw a best fit line. You don't play to connect the dots. You're not looking at that. You're looking at the general pattern. And that pattern's kind of spread out. That's why we're kind of right down the middle. Are we perfect? No. Are we supposed to be? Who can judge what perfect is? We're doing the best we can. So you look at this, and then you're going, okay, 2015. Well, this is years since 1999. 2015 is 16 years later. So look, they're going, each line is 2.5 years. 2 lines is 5 years. So 2000, that'd be 2014. Here it'd be like 2016 and a half. So 16 years later is what we're after. 2015, 16 years later. It looks like it's going to be about, oh, I don't know, about here. So your line of sight, okay, as we use these dotted lines to represent that I'm not drawing them, I'm just looking, should be, I'm looking up to here and I go, bam, that's where it hits. So then I look over here and my conjecture would be that, oh, in 2015, he should, if things kind of stay on their current trend, 5,000 points would be a reasonable, expectation for that year based on past performance. Okay? We're not guaranteeing it, but it's a reasonable conjecture based on what we see there. That's how we use scatter plots. That's how we draw a best fit line. Now, you can also, and again, math books they only give us limited amounts of points. If we were doing this in real research, we'd have a lot more data points. Okay, but like here, it says the scatter plot shows the number of cellular service subscribers in the U.S. Okay, now look, since 1999, I know for some of you, you weren't even born yet because it's 2021, so that's 22 years ago. So this only comes up to 2009 because it tells you it's based on our book, all right? So they drew a scatter plot. Those points line up really tight, don't they? They're not perfectly lined up, really tight. And it says, write an equation in slope-intercept form for the line of best fit that is drawn. Interpret the slope of the y-intercept. Now, here's what I want you to see. If I use that highlighter using the same thing, I'm going to use skinny highlighter, I think. Well, we'll go wider. You can see that if I'm looking at just this general pattern, right? Whoops. Hold on. Erase. Try that again. Looking at this general pattern, it's not real wide and spread out, right? And so they just kind of split right down the middle. In fact, they didn't have anything here in the first, it was the first year, it was right there. And so that's a good best fit line. You can see the pattern. So now, you see why the best fit line is there. That's how they got it. Let's look at just the best fit line. They want you to write this in slope-intercept form. So this goes back, this is what we're going to do, to be able to write a rule for a graph that we see, to describe it, a formula, if you will, an equation. So you know that it needs to look like this, that y equals the slope times x plus the y-intercept, all right? You can find all that on the graph, because look, it even says, we need to find the slope. We know how to find slope. The y-intercept, that's easy. Let's find that first. Just look here. It's right there between 75 and 100. Is it right in the middle? That'd be like 87.5. Yeah, I mean, I'm not gonna sit there and argue with you. You might say, "Oh, it looks like 90." Well, we can do that, but I'm just gonna go what's between 75 and 100, 87.5. Okay, so there's my intercept. It's actually 87.5 million, but it's in the millions. Now the slope. It says choose any 2 points on the line. They may or may not be data points. Okay, in other words, look at the line, don't look at the dots. What have I always taught you about the lines? Find obvious grid marks that they hit. There's an obvious grid mark right there. I'm looking, going, I don't know, I can't tell, I can't. Ooh, there's another good one right there. Okay, those aren't actual data points. They're our own dots, but we can find a nice tight slope here because look, what's the rise? Well, you went from 150 to 275 million, so it's 125 million people, from whoops, Mr. Ming not paying attention to what he's doing, and from year 3 to year 9 over 6 years. So your slope is 125 over 6. Now, since we're talking in the millions, you can write it that way. Okay, so I know the slope. 125 million people every 6 years. I could divide that out. It wouldn't hurt to make it a decimal, make it a mixed number, or I could reduce it down. In fact, we could approximate this. 125, 6 doesn't go into there nicely, so that's about 20.83 repeating. If you want, you could just round that up to what? That's about 21 million people per year, isn't it? Now, write your equation. So y equals, it changes by about 21 million people per year, so 21 times x, plus 87.5 million, whoops, 87.5, which is million, but we can handle that as we go. We're just working, we know this is in millions, because the subscribers is in millions, okay? So there, you've written the equation. Now, what they can ask you to do after that, okay, let's type that out, make it easier for you guys to see. So our equation basically looks like this. Y equals about 21 million times x plus 87.5, okay? Because that's what they started at in 1999. So it said, use the equation to make a conjecture about the number of cell subscribers in 2015. Okay, forget reading this out, because you can't. 2015, 16 years later, it's not on the graph. But you've got this. So, years would be from 2015, from 1999 to 2015, would be 16 years. So just put it in here. So you're going to work it out like this. Y equals 21 times 16. Whoops, I don't know why I put a space there. Plus 87.5 million. Okay? And if we do that, we come up with the following. Okay? 87.5 million, so we're going to do 21 times 16. Okay, we multiply that out. Let me go down here and do it. Should end up with y equals, let's see, 21 times 16, 320, 336 million plus 87.5, which will get us to y would be about, this is an approximation, so in fact, let me do this, because we know it's not, whoops, we know it's not perfect. It's going to be about, okay, if I add that together, I'm looking at 423.5 million subscribers. Okay? And that that seems reasonable. It might be a little high, particularly because we look at that, there is a limit, isn't there? This is in the United States, and right now in 2021, this is more than our population. So we know we're on the high end. But what caused that? Well, we rounded up to 21 instead of using 20.8. Okay, well, that would take off, if I do the thinking right, about 30 million people, which would still have us over our current population. But you see, this is, again, it doesn't guarantee you, it's just a reasonable conjecture. It's how, and the more data we collect, the more points we have, the more confidence we can have in our projection. Okay, and that's something we have to take into consideration. So there you go. That's how we draw best fits lines. That's how we use them to make predictions. So those of you that are virtual, you've got 2 sheets. They each have 3 problems each. In our Google Classroom, and you're open with Cami and do them, keep these around, it'll make it make sense. Those of you in the classroom, we're going to go over some of that stuff in class. Okay? Alright. So this is Mr. Mean, and we'll talk again. Best fit lines, here what they are, and how we use them.